Did you know that the Monte Carlo simulation, a complex mathematical technique, owes its name to a hub of games of chance? That's right, it's named after the Monte Carlo Casino in Monaco. This might seem like an odd connection at first, but when you delve deeper, it makes perfect sense. The Monte Carlo Casino is world-renowned for its games of chance, where the roll of a dice or the spin of a roulette wheel can determine a person's fortune. Similarly, the Monte Carlo simulation is all about understanding the impact of risk and uncertainty, much like gambling. In the simulation, countless scenarios are played out, each one based on a set of random inputs, similar to how each roll of the dice is an independent event. This technique allows us to make informed decisions in uncertain situations, just like a seasoned gambler at a casino table. So, the next time you hear about the Monte Carlo simulation, you'll think of roulette wheels and dice, not just data and statistics. The Monte Carlo simulation has a history as interesting as its name. Our journey begins in the heat of the Second World War during the 1940s. The Monte Carlo simulation was born out of necessity, conceived during the Manhattan Project, which was responsible for the development of the first atomic bomb. This simulation was the brainchild of scientists Stanislaw Ulam and John von Neumann. It was named Monte Carlo by Ulam after the famous casino in Monaco, as a nod to his uncle's penchant for gambling. The main objective of the Monte Carlo simulation at its inception was to assist in understanding complex physical phenomena like neutron diffusion, which was a critical aspect of the atomic bomb project. The simulation's ability to handle complex systems with multiple variables made it an indispensable tool in nuclear physics. After the war, the Monte Carlo simulation found its way into various fields, thanks to its adaptability. In the 1950s, it started to be used in the field of operations research, helping to solve complex logistical problems. By the 1960s, it had found a place in the world of finance, being used to predict the future behavior of financial markets. In the 1980s, the advent of computers gave the Monte Carlo simulation a major boost. With more computational power at their disposal, scientists could run more complex simulations, and the Monte Carlo method became a standard tool in fields as diverse as particle physics, statistical mechanics, and even computer graphics. Through the 1990s and into the 21st century, the Monte Carlo simulation continued to evolve and expand its reach. Today, it is used in a variety of fields, from predicting weather patterns and simulating traffic flow, to pricing complex financial derivatives and modeling the spread of diseases. From nuclear physics to finance, the Monte Carlo simulation has proven its versatility and importance over the years. Now that we know where the Monte Carlo simulation comes from, let's delve into what it actually is. At its core, the Monte Carlo simulation is a mathematical technique that allows us to understand uncertainty. It's named after the famous Monte Carlo Casino in Monaco, not because it's a game of chance, but because it uses randomness and probability, much like the roll of a dice or the spin of a roulette wheel. The Monte Carlo simulation isn't about predicting the future with absolute certainty. Instead, it's about exploring all possible outcomes of a decision and understanding how likely each one is. It's a bit like creating a map of the future, where each path represents a different possible outcome. Imagine you're trying to predict the weather. There are so many variables to consider: temperature, humidity, wind speed, and so on. If you tried to calculate all possible combinations of these variables, it would take forever. But with the Monte Carlo simulation, you can randomly generate thousands or even millions of weather scenarios, each one a unique combination of these variables. By analyzing these scenarios, you can get a sense of the most likely outcomes, as well as the range of possibilities. But the Monte Carlo simulation isn't just for weather forecasting. It's used in a wide range of fields, from finance to engineering to environmental science. Anytime you're dealing with complex systems with lots of variables, the Monte Carlo simulation can help. It can help investors understand the risks of a potential investment, engineers optimize the performance of a machine, or scientists predict the impact of climate change. The key to the Monte Carlo simulation is randomness. By randomly generating scenarios, it avoids the limitations of traditional forecasting methods, which often assume that the future will be like the past. Instead, it embraces the inherent unpredictability of the world and uses it to our advantage. In essence, The Monte Carlo simulation is a way to understand and predict the unpredictable. It may sound complex, but the workings of the Monte Carlo simulation are fascinating. At its heart, the Monte Carlo simulation is a mathematical method that uses randomness to solve problems that might be deterministic in principle. This method is named after the Monte Carlo Casino in Monaco, where games of chance exemplify the random processes that the simulation emulates. To understand how it works, imagine tossing a coin. Each toss is independent of the last, and each outcome, heads or tails, is entirely random. Now, if you were to toss that coin 100 times, the outcomes would start forming a pattern. This is the essence of the Monte Carlo simulation, using randomness and repetition to predict outcomes. The process begins by defining a model of the system you're investigating. This model includes all the variables that can affect the outcome. Then you assign a random value to each variable within its possible range. This is known as a random sampling of inputs. Next, the model is run with these random inputs and an outcome is calculated. This is one simulation, but remember, the power of the Monte Carlo simulation comes from repetition. Therefore, this process is repeated thousands or even millions of times, each time with a new set of random inputs. Over time, these individual outcomes form a distribution of possible outcomes, and that's where the magic happens. You can analyze this distribution to understand the probabilities of different outcomes. For instance, you can identify the most likely outcome, the worst-case scenario, or the best-case scenario. You can also quantify the risk by examining how much the outcomes vary. In a nutshell, the Monte Carlo simulation uses randomness to mimic the uncertainty inherent in many systems and repetition to understand the possible range of outcomes. It's like rolling a dice over and over again and using the results to predict what number is most likely to come up next. So, while the Monte Carlo simulation might seem complicated, it's really about using randomness and repetition to make sense of the complex. The Monte Carlo simulation is more than just a mathematical method, it has a real-world impact. Let's take a closer look at how this fascinating simulation technique influences various fields. To start with, in the realm of finance, Monte Carlo simulation is a vital tool in understanding the potential risks and rewards in financial markets. It helps investors and financial analysts predict the probability of certain outcomes and make informed decisions. For instance, it's used to determine the potential return on an investment portfolio over time, factoring in the inherent uncertainty and volatility of market conditions. In the sphere of engineering, it's used to predict the reliability and potential failures of a system under different conditions. It aids engineers in designing more efficient and resilient systems, from building structures to intricate machinery. In logistics, it's a game changer. The simulation assists in optimizing supply chain processes, inventory management and transportation routes, reducing costs and improving efficiency. Let's not forget about weather forecasting. Meteorologists use Monte Carlo simulation to model the weather patterns, taking into account the many variables that impact weather, like temperature, humidity, and wind speed. This helps in predicting weather conditions with greater accuracy, which can be critical in areas prone to severe weather conditions. But these are just a few examples of the many applications of Monte Carlo simulation. It is used in a wide array of fields, from nuclear physics to artificial intelligence, from environmental research to digital graphics. Each application contributes to our understanding of complex systems and uncertainties. The beauty of Monte Carlo simulation lies in its versatility and its power to transform abstract data into tangible insights. It allows us to approach uncertainty not as an obstacle, but as a factor that can be integrated into our calculations and strategies. Through its applications in various fields, the Monte Carlo simulation truly changes the way we understand and navigate the world around us. The Monte Carlo simulation has come a long way, and its journey isn't over yet. As our understanding of probability and randomness deepens, so does the potential of this powerful tool. We're looking at a future where Monte Carlo simulations could be applied to even more diverse fields. Imagine a world where city planners use these simulations to create more efficient public transportation systems, or where environmental scientists employ them to predict the impacts of climate change with greater accuracy. The possibilities are truly vast, from finance and engineering to healthcare and artificial intelligence. As our computational power grows and data becomes more available, The Monte Carlo simulation's potential for precision and complexity only increases. The horizon of Monte Carlo simulation is expanding, and with it, our ability to navigate uncertainty and make informed decisions. As we continue to explore the power of probability and randomness, who knows where the Monte Carlo simulation will take us next?